These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. Okay, what is light?
Electromagnetic wave.
So what's oscillating in the light?
Electric fields and magnetic fields.
Right. So we could draw the electric fields oscillating like this.
Mm-hmm.
And if we did that, which direction could the magnetic fields be oscillating?
In and out of the board or left and right.
So let's say it's like this. In that case, which way could the light be propagating?
In or out.
That's right, you can't tell from the information I've given you so far. Now, this is not what most light really looks like, because in most light, the electric field is oscillating in all possible directions around the direction of propagation. So what I've drawn here is what's called polarized light, which is not normal light. The light that we get from the sun is unpolarized light, or non-polarized light. So in non-polarized light, the electric field could be oscillating this way, and this way, and this way, and this way. So which way do you think the light is propagating?
In every direction?
No.
Oh.
It can only be, light can only propagate in one direction.
Okay, that's going that way. Well,
Which way could the light be propagating?
In and out of the board.
It has to be either in or out of the board. You can't tell which one, but the light can't be propagating up and down, because it has to be perpendicular to all of these.
Mm-hmm.
The direction of propagation has to be perpendicular to every one of these, so the only possibility is in or out of the board.
Don't the B field and the E field have to be perpendicular also though?
Yes, but the trick is there's a magnetic field that's perpendicular to this E that's oscillating horizontally. Then there's a magnetic field that's perpendicular to this E that's oscillating like this. Okay. And there's a magnetic field that's perpendicular. So it's not true that all the magnetic fields have to be perpendicular to all the electric field oscillations. That would be impossible. All that's necessary is that for each direction of oscillation of the electric field, there is a oscillation of the magnetic field that's perpendicular to it. So you can see why I can't really draw the oscillations of the magnetic field anymore, because they'd be right on top of all these electric field oscillations. However, on the other hand, the direction of propagation still does really have to be perpendicular to all of them simultaneously. And the only way it could be perpendicular to everything simultaneously is if it's going into and out of the board. Okay. So this would be unpolarized light, which is normal light from the sun or from the light bulb, and this is weird polarized light. So now, what is the direction of polarization of this light? Well, we could say it's polarized up-down because of the electric field, or we could say it's polarized left-right because of the magnetic field. So what's the convention? Well, it turns out the convention is just focus on the electric field. So what would we say is the polarization of that light?
Up-down.
Up-down. So it's conventional to kind of disregard the magnetic field when you're dealing with polarization. Not because it doesn't exist, but just because it's simpler to leave it out. So normally when you're dealing with polarization, you will normally ignore the magnetic field unless the question specifically asks you about it. If the question specifically asks you, you should, so suppose I tell you that this light is polarized up-down, then which way is the magnetic field oscillating? If the light is polarized up-down, which way is the magnetic field oscillating?
Left, right, or in or out?
Yeah, that's right. Left, right, or in or out. But if we know if it's propagating this way, then it would have to be left, right. So you can still figure out the magnetic field if you need it. But if they don't ask you for it, it's better just to focus on the electric field. All right. So if we have polarized light, unpolarized light, how do we make it polarized? Well, we pass it through a polarizer. And this polarizer is only going to let a certain type of oscillation through. So the polarizer has what's called a polarizer axis. Which tells you what type of light it's going to let through. So if we let this light go through here, what would the light through look like once it gets through?
Up, down.
Electric or magnetic?
Electric.
The electric field would be oscillating up, down. That's right. And is this now polarized or unpolarized light?
Polarized.
It's turned into polarized light. That's right. Which way is the magnetic field oscillating?
Left, right, or...
Yeah, so we're assuming in all of these that the propagation is into and out of the board. So if you had to, so notice this doesn't tell you the type of magnetic field that's going through, not directly. So it's just the convention that the axis of the polarizer refers to what type of electric field it lets through, not what type of magnetic field. So you know what it's like is, let's say I had a rope in my hand and the other end was on the wall over there. And I started shaking my hand up and down and left and right, and diagonally sometimes. So you would see a whole bunch of different waves going from my hand to the wall, sometimes up, down, sometimes left, right, sometimes diagonally. That would be like unpolarized rope. But then, let's say that I put a picket fence between me and the wall, and I thread the rope between the slats of the picket fence. Well, notice I could still be shaking my hand in all kinds of different directions, but once the rope goes through the picket fence, it's only going to be oscillating up, down, right? So the picket fence is like an analogy for what the polarizer does. So here we could call this I0 the original intensity. Do you know what the intensity of this light will be compared to I0?
I0 cosine squared theta?
That turns out to be something different. That applies when you take one polarized light and turn it into a different polarized light. Here we're taking an unpolarized light and polarizing it. Well, all of these...
right? 2I naught or something?
So this would be 2I naught?
Yeah.
So should this intensity be bigger or smaller than the original intensity? Why bigger?
Because now all the lights are... Am I wrong?
Yeah.
Oh, okay,
so
small lights.
is this going to let is this going to let all the electric field through or only some of it?
Only some.
So there's no way it could be getting more electric field than before. A polarizer is a subtractor, not an adder. It's only letting some through. Notice every single one of these oscillations could be split up into horizontal and vertical components. Every one of these oscillations has horizontal and vertical components. But this is only letting half the components through. It's only letting the vertical components through and none of the horizontal components. So it turns out that...
There's 1/2 I.
Yeah.
Okay. So I got the 2.
So it'll let half through. So when does this equation apply? This applies when you start with unpolarized light and polarize it for the first time. This is a different equation than the one you were thinking of a second ago, but this sometimes is tested. Okay? Now, let's say we take the light that has been polarized and we put it through a polarizing filter. Well, let's say you let it through this filter. So first of all, what do you think would be the direction? What would be the direction of oscillation of the light after going through that filter?
Up, down?
Up, down. And how much of the intensity is going to get through?
All.
Yeah, in this case, all of it's getting through because this won't subtract anything because they're already aligned with each other. Now let's say we take this light and pass it through this filter. How much of the light will get through?
0.
0. So how would you draw it? Well, you can't really draw it. It's like a dot. There's no oscillations. So what's the new intensity?
0.
Yeah. By the way, how is intensity psychologically perceived?
Brightness.
Brightness. So this would be no light at all. And this would be just as bright as it started. Okay? Good. Now, let's say that we start with this light and pass it through this filter. Will this let some light through or 0 light through?
Some.
It will let some. A lot of people think that it's 0 because this is not pointing the same direction as this, but this still has a component that's along this direction. So this will let through the component of the light that is parallel to the filter over here. So it will let through a component even though it won't let through all of it. So will the new intensity be higher or lower than the old intensity? Lower. Lower. All right, so what's the equation for figuring out this intensity?
I equals I naught cosine squared theta?
That's right, this is called the Law of Malus. Try to draw on your paper what angle theta is.
I know it's an angle between, is it this angle?
So, theta is the angle between the light and the axis.
Okay.
Theta is the angle between the polarization direction of the light and the polarization direction of the axis. Does that help you? So which angle is that?
So between the polarization, the axis, which is this, right?
That's the axis of the polarizer.
And the light.
And which way is the light oscillating?
Up, down.
So what's the angle between those directions?
So this is,
Okay, is that what you were showing before? I'm not sure. Okay.
but I wasn't
So
sure.
the way I would do it is like this. I would draw this line, and I would say this is the angle. So is this theta?
No.
Not on this problem. But remember how we saw in Snell's law, they oftentimes try to trick you by giving you the wrong angle. So you have, or by asking you about a different angle. So remember, not every angle is the angle that you need for theta. You need the angle between the oscillation direction and the polarizer direction. Does this make sense? So will I1 be bigger or smaller than I0?
Smaller.
Because cosine squared is always less than 1. Right?
Less than or equal to 1, right?
Less than or equal to 1,
yeah,
that's
so
right.
then, yeah, the greatest of these will be I naught.
For example, what would theta be in this case?
0.
And do you know what the cosine of 0 is?
1.
So this then would give us this answer, which we already said made sense. This will let all the light through. And what would theta be in this case?
180.
No, try again.
90, sorry.
90. You could say this was 180,
Yeah.
really. And what's the cosine of 90?
0.
Which confirms that Malus's law would give us this answer here
Right.
as well. Okay? But this also works for other cases besides the extreme ones. Okay, let's try this.
So the angle between the axis and the light would be 70 degrees. So then I1 would equal I naught times cosine squared 70.
Okay.
Will be less.
Do you have a calculator?
No. So it's going to be 100 times 0.117. So it's going to be 11.698.
So what's your answer?
Like 11.7 watts per meter squared.
Okay. Which is less than 100. So the trap here that I was trying to get you to plug in the 20, but you didn't do that. You used the correct angle. Okay, good, good. Can you think of anything else that you might figure out now at this point? From intensity?
Like
what have we learned
power?
that we could figure out from intensity? Power is a good thing, but we need to know an area for that. Can you think of anything else that we've learned that we can figure out from intensity?
You can figure out the amplitude of like the E or M.
That's right.
B field.
Why don't we do that? So let's figure out, because we haven't practiced that for a while. So let's figure out the amplitudes.
Okay.
Let's try that on the tablet when you're ready.
Oh yeah, I forgot. Let me get the equation. So average intensity equals E. And we know that our U intensity is 11.7. U naught, which is...
So you'd be given that on the test. That's 4 pi times 10 to the negative 7. In SI units.
So then, and then E. So and this is in meters per. I think maybe in meters.
Okay, you lose a little credit for the units. Those are not the units. What does E stand for?
It's. Wait. Oh. Okay. It's the amplitudes. Okay. This would be Teslas.
Yeah. So magnetic field is not in meters. It's in
And
Teslas.
this would be coulombs per meter squared.
Looks like you might have forgotten what the units are for
Yeah.
electric field. Those are newtons per coulomb. That would be a good thing to have memorized. You can put that in your cheat sheet, but I think it's important to memorize the units. So that's newtons per coulomb. Okay. And it's not really because they're amplitudes, it's just because one's an electric field and one's a magnetic field. Okay, so generally the graders are going to want to see the correct units on those answers too. Okay, good. So if you haven't done so already, you should be making up your cheat sheet for the test that's coming up. So you want to include these formulas in that for yourself. Okay, good. Should we be worried that B came out so small? Remember we talked about that a little, that's just an artifact of the units. Since C is 3 times 10 to the 8th, B has to come out much smaller than E when you use this formula. Okay. Okay, so we hadn't practiced that for a while. So that's something else that might be tied into a polarization question. So we've gone over 2 different equations for polarization. How do you know when to use this one and when to use this one?
So use the first one when, like, they're both, you're using when you start with polarized light, and then you go into polarizer. And the second one is when you start with unpolarized light, going through polarizer.
So when the original light is already polarized, you use this one, and use this one when the original light is unpolarized. It's possible that you could see a problem where you have to use these more than once. You could take unpolarized light and put it through a polarizer, and then you could put it through another polarizer. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.